What if I told you there's a single secret number that pretty much unlocks all of chemistry? It's called the mole, and honestly, it's way, way simpler than it sounds. So let's dive in and break down chemistry's most important counting tool. We all know what a dozen is, right? It's 12 of anything. Eggs, donuts, bananas, you name it. It's just a word for a number. Well, chemistry has one of those too, but it's for counting atoms. We call it a mole. So that leads to the big question. Just how many atoms are in one mole?
Get ready for it. That's the number. It is so ridiculously huge, it's almost impossible to picture. We write it as 6.022 times 10 to the 23rd. That's 602 sextillion. Now, this isn't just some random number. It has a special name, Avogadro's number, and it is the absolute key that lets us count things that are way too small to ever see.
So here's our game plan. First, we're going to really lock in that chemistry's dozen idea. Then we'll connect that giant number to something we can actually measure in a lab, mass. After that, we'll see how the mole helps us count particles, measure gases, and even run entire chemical reactions. And finally, we'll tie it all together and see why this is so important for your exams. All right, let's jump right into part one. We're going to start with that core idea. Just think of the mole as chemistry's dozen. Okay, so officially, what is a mole? It's the standard unit we use to talk about the amount of a substance. It's basically how a chemist answers the question, hey, how much stuff do you have in that beaker? But on an atomic level. And really, this is the best way to wrap your head around it. A dozen is 12 things. A mole is 6.022 times 10 to the 23rd things. The number itself is massive, but the concept? It's exactly the same. We just need a much bigger number because, well, the things we're counting are just unimaginably tiny. So that special number, 6.022 times 10 to the 23rd, gets a proper name, Avogadro's number. And here's the most important takeaway about it. It is a constant. It doesn't matter what you have. A mole of carbon, a mole of water, a mole of pure gold. It's always that same exact number of particles. But what do we mean by particles? Well, pretty much anything. We could be counting individual atoms, like in a chunk of sodium. Or we could be counting whole molecules, like H2O molecules in a drop of water. It even works for charged ions or tiny little electrons. That's what makes the mole so useful. It's a universal counting tool. Okay, so counting trillions upon trillions of atoms is a cool thought experiment. But how does that actually help us in a real lab? Well, this is where things get really clever. Let's connect this abstract, massive number to something we can physically put on a scale, mass. Now this right here, this is probably the most beautiful shortcut in all of chemistry. On the left, you've got atomic mass. That's the weight of one single tiny particle measured in a teeny tiny unit called AMU. On the right, you have molar mass. That's the weight of a whole mole of those same particles. And here is the magic trick. The number is the same. One water molecule weighs 18 AMU. A whole mole of water molecules weighs 18 grams. That's it. That's our bridge from the invisible atomic world to the world we can actually measure. So molar mass is just the answer to a very practical question. If I need 1 mole of this chemical, how many grams of it do I need to weigh out? The unit, grams per mole, tells you everything you need to know. So how do we actually use this? It's a super simple 3-step process. First, you take the mass you have in grams. Let's say you have 36 grams of water. Step 2, you find its molar mass from the periodic table. For water, that's about 18 grams per mole. And finally, you just divide. Your given mass divided by the molar mass. So 36 divided by 18, boom, you have 2 moles of water. It's really that easy. Awesome. So we've built the bridge from moles to mass. But guess what? The moles toolkit is even bigger. Let's see how it also lets us count the exact number of particles and even measure the volume of gases. And this next part, it's super logical. If you already know how many moles you have, figuring out the actual number of atoms or molecules is a breeze. You just multiply the number of moles by Avogadro's number. It's just the reverse of what we did earlier. Simple as that. Now, the mole has another really cool trick up its sleeve, but this one is exclusively for gases, and it only works under a specific set of lab conditions that we call standard temperature and pressure, or just STP for short. And here's the special rule. At STP, which is 0 degrees Celsius and 1 atmosphere of pressure, 1 mole of any ideal gas will always fill up a space of 22.4 liters. It doesn't matter if it's hydrogen, oxygen, or neon, it's always 22.4 liters. This idea, called molar volume, is a massive shortcut for chemists.
All right, now for the main event. Let's talk about the place where the mole becomes absolutely essential: chemical reactions. You can think of the mole as the key that lets you read and understand the language of chemistry itself.
Honestly, the absolute best way to think about a balanced chemical equation is to see it as a recipe. It's not just a boring string of letters and numbers. It's telling you exactly what you need and what you'll make. But instead of measuring in cups or tablespoons, a chemist's recipe measures everything in moles.
Let's look at the classic recipe for making water. See those big numbers out front? Those are called coefficients, and they give us the ratio. This recipe is telling us we need 2 parts hydrogen gas to react with 1 part oxygen gas, and that will produce 2 parts water. Now, here's the crucial part. Those parts are really moles. So 2 moles of H2 react with 1 mole of O2 to make 2 moles of H2O. That is the mole ratio, and it's everything.
And this whole process, using these mole ratios from a balanced equation to figure out how much stuff you need or predict how much you're going to make, that has a fancy name: stoichiometry. It sounds complicated, but it's really just the math behind our chemical recipes, and it is built completely on the mole concept. So that brings us to our final, and maybe the most important question of all. Why do we care? Why is it so critical to master the mole? Not just for passing a test, but for actually getting chemistry.
It's because the mole is the central hub. It's the one concept that connects everything we can measure in chemistry. It's what lets us jump from the mass of a substance to the number of particles inside it to the volume it takes up as a gas. It's the tool we use to read chemical recipes and predict what will happen. To put it simply, without the mole, there is no quantitative chemistry.
And look, for all of you who are studying for big exams like NEET or JEE, here's the bottom line. The mole concept is the absolute foundation of physical chemistry, and it is always one of the most important, highest-scoring topics you will see on that test. Getting these calculations right translates directly into a higher score, period.
So there you have it. The mole is a number. It's a bridge between the world we can see and the world we can't, and it's the very language of chemical reactions. With this framework, you have all the tools you need. So, are you ready to tackle those stoichiometry problems? Of course you are.